Ganil and visited some friends, and I'd like to thank the organizers, Pete, Rick, and Marek, for the opportunity to tell you a little bit. I hope, nevertheless, to convince you about the exciting things about pairing in nuclei. You probably already noticed, I always like to have a little intro here of who am I. You may notice some of a connection with Niccolo. Actually, if you look, there is an extra C in the spelling of our name compared to that. I haven't figured that out yet. So whoever figures this out, I'll send you a bottle of my favorite Chianti, the Machiavelli one there, which is actually, as you see, written with only one C. So, yeah.
Maybe the second C is for cute?
I don't know. Maybe. A charming prince.
Charming, yeah.
So in any case, maybe it's because of an extra Chianti, CC. So nevertheless, the outline of the talk today, this may be very ambitious, so I may have to renormalize here as we go. We have another lecture Thursday, and so I may have to postpone some things that I plan to do today, tomorrow. We do have the hands-on activities in the afternoon, so I try to pick there. But there'll be a short introduction and then a few things that already were discussed during the week, but I try to sort of repeat them in line with the topics that I will discuss. Look into the pairing and aligned coupling schemes, which are at the core of the major ingredients of nuclear structure. We discuss a little bit of rotational properties, which you have seen already also during the week. And then we look in detail at the pairing phase transition with the activities this afternoon, solving the 2J shell model. It goes a little bit beyond to what you've done already with Pete on the single shell. So I guess you probably have had introductions this week. I think atomic nuclei offer a very unique quantum system, and it has many, many common phenomena with other subjects of contemporary research in physics, notably mesoscopic systems in condensed matter and atomic physics. And I think in particular for us in nuclear physics, these are actually exciting times because there is a convergence of new instrumentation, new accelerators, one of which is sitting right here at Ganil, where new exotic nuclei are being produced. But once you produce the nuclei, you have to detect them and study, and new instrumentation also. Are they having a tour of the facility? They had. So you've seen many of these new instruments which increase the resolving power, and although they will help answering some of the questions we have now, which is more important, as is always the case, they will find new phenomena that we didn't anticipate. And I think as part of the this talent class, I think there's been this synergy now between new theory developments. People are doing now things that were never dreamed of many years ago. There is now this predictive power in theory and some kind of a synergy between experiment and theory to guide the progress in the future. You've seen this landscape. This is where we sort of play in nuclear physics. It's a great chart, and we are at the moment exploring the limits. There is the limit of isospin, where we move towards the neutron drip line, or the proton drip line. There is the limit of existence in terms of super heavy elements. And of course there is also another ingredient, which is excitation energy and angular momentum, that we'll also discuss briefly during the lectures. And as you probably know from your own studies and from lectures that you heard before, there is a lot of structure physics playing roles, not only for the sake of the properties of the nuclei, but because of the paramount importance of that structure in astrophysics, for our process, stars, supernova, nucleosynthesis, and therefore the properties of nuclei at the streams will be of very interesting determining some of these processes. And there is many structural things that you probably discussed already, but particularly the neutron drip line, where you expect that somehow the neutron wave function, because it's weakly bound, will tunnel new phenomena related to coupling to the continuum, and of course pairing plays a major role in this region. Also in this region, and you have also, I guess, addressed some of that in Pitt's and Rick's talks, there is the question of T equals 0, or neutron-proton pairing, for which the structure of these nuclei along the n equals c line are very relevant.
I left this entirely to you, actually.
Oh, okay, so we'll discuss that too on Thursday. And of course, the question of shell stability in the island of super heavy elements, for which also pairing correlations play a major role. So, pairing sort of underlies many of the structure properties, and that's the topic of these two lectures. It all started actually for nuclei in 1958, just shortly, less than a year after Bardeen, Cooper, and Schiffer proposed the VCS theory of superconductors, when giants of our field in theory, Bohr and Mendelssohn, together with the solid state fellow Dave Pines, came up with an analogy exactly very similar to the concept in electron superconductivity, by noticing that when looking at the states in even nuclei excited from the ground state, they noticed that the distance in energy between that and what you would expect for a odd system was several times larger than just the rating of the pair. And therefore, they concluded that there was this correlated state of nucleons similar to that of a VCS superconductor, and that started the whole business of pairing in nuclei, which is still very timely today. And of course, many properties, not only that gap that we see there, but as we will discuss this week, you know, or even mass difference, rotational moment of inertia, and many other things that I'll show you, depend on pairing correlations. And of course, as you see, and we discussed, there is common to other fermion systems, as I said, in mesoscopic system, but notably, you know, superfluidity, and in particular solid state and atomic physics, quantum dots, etc. Now, 58, so it's more than 50 years already. I cannot even attempt to cover this field in 2 lectures this week, but I hope that I will be able to convey to you the excitement of this particular topic, and perhaps you get excited too, and then you will contribute to the development of these particular aspects. Now, fortunately, I have help, but I was worried that the task was so big that I worried before accepting the talk to step on those big shoes when Pete asked me, but nevertheless, I accepted the challenge, And, but as I said, I have big help because there is a recent book by Ricardo Broglie and Dave Brink on nuclear superfluidity. This is a nice volume that I recommend to add to your list of books if you are interested in the aspects of pairing. I think I will attempt covering some of these aspects, but if you want to get back to some more detail, that's the book that you should have. And also a recent volume which actually commemorates these 50 years of what is called nuclear BCS. There was a 50 years of BCS volume focused on superconductors and these aspects, but Broglie and Selevinsky this time edited this is a series of articles on the application of BCS to nuclei, very, very timely and relevant for these discussions. You guys probably would like to have a copy too, or ask your advisors to have that in the department where you work. Now, of course, this is specific to nuclear pairing, but I'm sure you have already perhaps been exposed to some of these books. I just give you also for reference some others that here you should have in your library, and you may have already seen some of these. There is some of the classic books, perhaps a little bit too advanced, but those of you who will be theorists, I guess, will be exposed to this. And then there are a few articles, review articles that address the question of pairing, the original Bess Sorensen work, Broglie and company, and a more recent one by David Dean and Morten Georgensen, who also address some of the contemporary problems of pairing. So this is sort of the introduction. We'll go a little bit more in detail, and I will capture a little bit of things that were discussed during the week. Please, if you have any questions, feel free to stop. I hear that you do that, so I encourage that. I think it's better if you learn something than just going through 70 slides and then you don't get anything. So the concept I will start is that with shell structure. The analogy with atomic physics is one where you say, well, how difficult it is to excite a system, how high is the excitation energy, gives you an idea of how rigid that system is. And then you can go to the National Nuclear Data Center in Brookhaven, for example, and get this nice plot. And you ask yourself, what is the excitation energy of the lowest 2+ state, and you plot that as color-coded, and maybe you show that. Did you guys show it? I showed it. So then you see clearly there are particular numbers where it costs you a lot of energy to excite nucleus. That indicates that those particular nuclei are extremely robust to excitation, similar to the noble gases, and therefore there is an indication of some kind of shell structure which is present. Now we will see later that if pairing was so strong that will dominate over shell structure, this will be kind of bored, sort of not uninteresting landscape. But shell effects are strong enough to survive pairing interaction in the still there, as you can see. That doesn't mean that there is no pairing by any means. It's just that pairing is not enough to overcome. And that's at the core of the pairing phase transition we discussed today. Now, of course, I'm stepping in uneasy territory here, and I worry that Professor Kasten here will feel that I don't appreciate the subject of shell model. I'm not an expert, of course. I'll try to convey to you the way that I see the problem in a simple way that I'll try to capture the ingredients for what we discuss later. So, you've seen this perhaps already. The approach that I'm going to take is not the most ambitious one, which is the one carried out by a large effort in theory, which is to solve the Schrödinger equation of these A nuclei interacting by some kind of two-bar interaction, even three-bar interactions in an ab initio form. And I heard you have discussed that this week with Mark Caprio. There are approaches today that attempt to do that, and you can do it, in fact. It's amazing that you can, I believe you discussed rotational properties of light nuclei coming out of solving the Hamiltonian with no approximation, just the fact that you take some kind of two-bar interaction and solve it all. So what you've done this week and what I propose here is the classical shell model approach. We somehow rearrange this sum into a part here that sort of describes the motion of these nucleons in a mean field, which is nothing but the average of the two-bar interaction of the other nucleons on one particular one. And then, of course, what we put here, we subtract from there, and this is what we then refer to as the residual interaction. So we have a core with a mean field, and then you treat the residual interaction in some aspects that is either effective or semi-microscopic, or the way we are going to sort of do it for the discussions today is sort of somewhat phenomenological approach. Yeah, this shell model business, we take it for granted, but actually is very profound. And many of the giants in the field have thought about this. Why is it that nuclei can be described as a shell model, like say in an atom, where you have a clear field and the electrons moving around. And it turns out that Ben Motteson have presented some arguments based on the so-called quantality parameter, which if you look at a potential, and here is described for nuclear, but you can imagine of any system, there is a scale given by the attraction, in this case V0, and a size given by A. So you ask yourself, what is the quantum fluctuations, namely the kinetic energy of the zero-point motion compared to the strength of that interaction. And if that number is actually very small, as you see here, that means, for example, that you are more like a solid. Fluctuations due to the kinetic energy are not enough to overcome the V0. But in nuclei, they are comparable, in fact. And that makes this more like, as you see here, a number which is closer to 1. These two become comparable. And this is a liquid. Now, it's a quantum liquid, and the concept of quasi-particle works. The fact that the Fermi motion and the Pauli principle allow you to talk about an orbit, and the fact that you can describe that in a mean field may be at the root. And in fact, I have posed the questions to some of my theory colleagues, actually more in particular. I think this is a nice quantity that should be studied as we move out of N=C into the weak binding region. What is the quantality parameter as nuclei move? Is there kind of a signal in that parameter, the kinetic energy over the potential as you become weakly bound? So this is something that to keep in mind. Why is it that we are describing nuclei in this way? So you've been introduced here to the mean field. This is one characteristic of that in the form of a Wood-Saxon potential. You have orbits, of course, given the nature of the problem, and these are the shells that we see in that plot of the 2 plus energy. Now, if you were to start with a simple harmonic oscillator potential that is always being used as an approximation for a Wood-Saxon potential that will be more realistic, then you get something like that. It's a simple problem, but it's very nice to work with, and people have used this. And then you find out that, that the light system, it makes sense, but as you move heavy, it starts to deviate, and of course what Pete was discussing just now about the spin-orbit splitting is the key element who was proposed by Maria Gopper-Meyer and Jensen, who was the Nobel Prize, and the spin-orbit splitting is an effect that depends on the derivative of the potential and makes the high spin of the L equals, in this case, H pair split in a way that the shells that are characteristics of the harmonic oscillator and scale, like 41 to the square cube root of A MEV, get modified by the spin orbit splitting. Now, because the harmonic oscillator is not really as rounded as flat like this, people have added an L squared term to make it flatter and depend a little bit on L2, because otherwise the ordering of the L is not preserved. See, people have talked about the fact that because the spin-orbit splitting is the derivative of the potential with respect to R, if you go to a region where you have weakly bound nuclei, then the surface of that nuclear becomes more diffuse, and therefore you would expect some effects on the spin-orbit splitting as you move away from the stability line. Wave functions, for example, which are used in that case, showed here that, for example, the harmonic oscillator, which is this potential, as we discussed, parabolic here compared to the Wood-Saxon, but the wave functions resemble one another. Of course, when you go to weakly bound nuclei, that may not be true anymore. That's one of the challenges the ab initio people have, because you have to take into account that if you have orbits that are very close to the lip, there is no lip in the harmonic oscillator and it's no tunneling. So that's a serious problem when you go to very exotic nuclei to address that, and I imagine that Mark has mentioned that in his talk. Okay, so these are the ingredients. We go back to our shell model framework. This average potential, as I said, is the average of all the others in a way, and therefore you have that mean field. You parameterize that. You assume that there is a core, one of those particular nuclei which sit in the double closed shell region in that table, where both neutrons and protons are well described by an innate core, and then you have the Hamiltonian of two particles, in this particular case, say either a neutron or two neutrons or two protons, with some interaction between the two. We write this sort of schematically, but that can be cast if I take that expression that I had before and rearrange it. You can think about this yourself when you get a copy. And then you can see that indeed the Hamiltonian here, after rearranging this and relating to the fact that this is indeed what you expect very close to be the average potential, you end up having this expansion here. Core, single particle, and the interaction between those two. We can excite the core because I show you the 2+ energy of those nuclei, so it doesn't mean that these are completely inert. So this approximation of having a core and the particles outside without affecting the core may not be so. But thanks to the fact that the excitations of those could be cast in a form which is something 2 times the, if you like, the excitation energy of the harmonic oscillator. This term is large compared to the residual interaction, which is about 50 MeV over A. That's, you can, maybe we'll do that as an exercise this afternoon. Think about it, and then you show me why that is. But so essentially, this can be perturbably treated, and therefore it's not so bad that you can take the core as an inert core. Then, of course, there are refinements of that, and people have done that. In particular for pairing, as I'll show you on Thursday, this core polarization is actually extremely important. But for the moment, we assume the core is there. And note here that if I were to make this ratio, it turns out that the effective interaction divided by the separation scale as 8 to the 2/3. So this effect may become smaller and smaller. So I think that tells me that, for example, calcium 40, at least we should discuss this if you guys agree, but calcium 40, which is 2020, a closed shell nucleus, is actually less magic than lead-208. So my argument is that the residual interaction actually diminishes with the size faster than the shell. That goes like 8 to the 1/3. And although there is a degeneracy, so lead-208 is the more close magic nuclear than calcium 40. In fact, calcium 40 is not a very nuclear, but nevertheless, think about it. We can discuss that in the afternoon.
There is a little misprint on transpose 8 minus 2/3.
Oh, well, it says decreases. So, but yeah. Okay, so now, residual interaction. That's the aspect that we are going to address from now on. And you have chat about that at length probably this week. I'll give you a little take of my own on this subject. So as I said, you can derive that from basic principles, the nuclear-nuclear interaction. You do all the things that you have to do there to take into account median effects, and people are doing that. As I said, the ab initio methods allows you to do that, effective field theories, approaches, etc. You can actually determine the residual interaction from experimental data by using that expression that I assume I have a core. So then I can go to different cores and determine for the 2 nucleon system, so take calcium 40 plus 2 nucleons, or lead-208 plus 2 nucleons, and I can locally determine empirically the effective interaction of those 2 nucleons, and then learn about the properties of those 2. Pete, I think, already alluded to that with the example of the lithium-6 and helium-6. In fact, I'm going to propose to you to estimate the strength of the pairing from helium-6 and see what we can say about pairing in heavy nuclei if we were to extrapolate from helium-6. And then once we have these, you can input that into a big shell model code that takes into account those basic matrix elements, and then do all the algebra related to that Pete, I'm sure, already discussed. And I guess you have already some tools in the ARC model program that allows you to do that and do more complicated systems. There is another approach, which is also, once you know about the residual interaction, you can then use a schematic model which captures the main ingredient of that interaction in one form or another, and for which there are tools to solve the many-body problem either exactly or numerically in a simple way that allows you to treat more complicated nuclei. So we will look at these 2 now in the rest of the lecture. So 2 references that come to mind, which I always like in this aspect, is a famous paper by Schiffer and True, and actually one that is not as well known, but the fact that Hans Blaether was there makes it important to me, and which is how to derive that effective interaction from experiment. And essentially the approach is that the one that Peter was alluding this morning. You can do that in a more complicated way when you go heavy, but essentially you look at a core with closed shells, again, lead 208, for example, then you go to bismuth 209, and lead 209, those are the one nucleons. You determine the binding of that proton or neutron in that core, and then you look at the Odot system, in this case that has the Na or PP or NP, and then you take that, and then you calculate the binding difference, which tells you how much of a residual interaction you have for that J1 and J2. Because you have the different couplings, so you can couple, say, two particles, one in J1 and J2 to a multiplet of spins, you can actually calculate a Schiffer parabola and use a normalized way to present that, as I will show you next. So here, and it's very intuitively actually to present the results in the form of an angle. You imagine yourself, you have these spins, and these orbits tend to be perpendicular to that angular momentum, and it's indicated by that, and then you can calculate the angle in a sort of semi-classical way by looking at the coupled spin. So you couple those two to J, and then using that and information on J1 and J2, calculate an angle, and then look at the dependence of this interaction as a function of the angle. So because we know the nuclear interaction is short range, you would expect that this will be maximized when? If I have these angles, when will be the maximum?
Maximum overlap.
Maximum overlap, indeed. That's the concept, and this angle gives you that overlap visually immediately, and therefore when you plot, for example, now t equals 1, the t equals 1 stays that T showed earlier, for example. Now I go to many nuclei here, you see P3 half, that's pitch scales, and then P3 half, etc. And then what you see, indeed, that when you have 180-degree coupling, namely one particle going one way, the other one, but maximum overlap imposed by the Pauli principle for equal nucleons, then the energy is quite binding. So already there tells you that the nuclei like to pair. So the nuclear interaction already favors the formation of pairs. Now, as you open the angle, the interaction becomes less bound, and then there is this sort of trend that favors the 180. What happens on the T equals 0 channel? Now you can couple both the neutron-proton to T equals 0, T equals 1, example we just discussed. Now for that one, you can still couple the neutron-proton pair, of course, at 180 degrees. That also gives you maximum overlap. But also you can now couple, because they are not bound by the Pauli principle, you can also couple them to high spin, which are extremely important for the isomers you guys just discussed before. You can have, say, a d phi half neutron and a d phi half proton and couple them to 10. They overlap very largely, and therefore they actually bounce even more. So the T equals 0 in the high spin state is even stronger than that of the pairs. So that's the property of interaction in the T equals 0, J equals 0. So if you look at either Schiffer or the other paper by Molinari, then you can convince yourself that a major ingredient of this interaction that explains this is a delta function, so-called short-range interaction, like you discussed this week and week before, that likes this strong overlap with some constant G that will be the strength of that part of interaction. But that's not all. In fact, you cannot describe all the data without a longer range force. Now, and that usually parameterized by the Legendre polynomial of order L. And the strongest term that comes out is the quadrupole term. And that is so-called the quadrupole correlations. And actually, the range of this in angle is, this is infinite small, this one is larger, and that gives you the seed for quadruple deformation that you have seen already during the lectures this week. And the parameters that Molinari quotes are about 20 MeV over A and 50 MeV over A for those parameters. And we will look into that a little bit more as we move forward. Actually, I have G and G and V2 like a energy scale divided by A. Why? Why should it go like 1 over A? Why shouldn't it go like A?
What is the question? Okay.
So, if you were to repeat the analysis of Molinari and Schiffer and True, and you look at the strength of these matrix elements, or the strength of this interaction that I put here, you find that they scale like 1 over A. I mean, not completely 1 over A, but they decrease with A. Now I show you here a plot from another nice report of Dennett, where he shows this average energy that I showed at the beginning, which essentially gives you the size of that matrix element. And you see that for the P3 half here in lithium is very large. Then when you go here to 200, this goes down. And the question is why? Well, you answered earlier about the reason why it's strong. What was that? The short range, yeah?
Yeah, but I don't know, because the volume goes as A.
Yeah.
But
So
the distance between the particle doesn't go as A. It stays more or less the same.
no, if you have a volume which is bigger,
No, the average distance between the nucleons is more or less the same. They're like some hard to figure somehow. The distance between neighboring nucleons.
no, they will go like if you have a bigger size.
No, the nearest neighbor is always more or less sitting at the same distance, above something.
Well, I propose to you that you calculate a matrix element when you have, say, a delta interaction, and you assume that they have to interact when they are on top of each other, and then you calculate the wave function of that nucleus in a simple approximation, then the probability of finding is 1 in the total volume. Therefore, the probability of finding one and another one close by goes like 1 over the volume. You have a bigger volume, the chances that these two nuclei interact.
But we have also more nuclei.
What?
We have also more nuclei.
Yeah, and then we will see that goes, because then the energy, which is then the Hamiltonian, of course, takes into account that you have more, and that's exactly what we are going to discuss now. So, for example, if you have a quadruple interaction, you are going to have the probability of interacting more because you have more neighbors. You have a delta interaction, you saw that it only interacts with the near because it depends on the number of pairs. And actually, you can actually calculate the volume is R squared and say, and that actually, you see, this is 1 over A, the red line here, which is a little bit stronger than, in fact, if you take the harmonic oscillator wave function, you may get like it's more like A to the 1/3. He determines 3/4. So the average strength scales like 1 over the size. So if you have a, let's go ahead again, as we argue, and that actually goes back to So the average mean field is the sum, as we wrote it schematically in the beginning, is the sum of this average Bij, and so you have A average Bij, because you have 8 nucleons, and you know the depth of the potential is constant, it's about 50 MeV. So this means that the average interaction should go down 1/8. Okay. So when do we? Oh, 10:30. Okay, very good. So let's go now and take advantage of what we just learned about the nature of that residual interaction and try to see what kind of coupling scheme will be favorable for us to take advantage of that. How do the nucleons will couple in order to maximize that overlap? And so I think you have probably discussed this with Pete already. And essentially, as we argued before, based on the parabolas or the curves of Schiffer and True, we see that the maximum overlap occurs with 180-degree coupling to a zero. And if you were to write down a wave function that will look like that, you will have some kind of harmonic oscillator, Legendre polynomial wave function angular, which will depend on the L0 coefficient here, and then this sort of looks like that. So they like to concentrate in a region here that depends on the L, the larger the L, the more concentrated they are, and they take advantage of correlations on radius, which are of the order of the radius of the nucleus divided by L. So you can see immediately that as you open up, then the distance here becomes I R over L. So then any state that is not the 0 class essentially becomes unfavored, because the distance on average now increases beyond this region where the delta acts very strong, and therefore when you have an attraction like that, and then this you saw, I'm sure, with Pete about the seniority discussions and the delta that we just heard this morning in the example, you imagine and you can look at that 210, for example, two neutrons above 126, the closed shell, and then you see this sort of pattern where the 0 plus is depressed compared to the rest. And when you look at the spectrum, and now you know how to calculate that with the delta, you'll see something which resembles that. And I don't know how to do that, so we'll do sort of a simple pairing interaction. We just assume a constant matrix element that I still call G and the delta. So essentially what you do is you just project, and only the 0 plus goes down, and then you make all of them degenerate, and then this one, and in that way it's very simple to solve the problem, because your ingredients here in a single J, as you know that, probably you know it better than I do now. You have n particles in a J with a degeneracy omega. You like to make those pairs, and then your wave function is essentially a creation of those pairs in the ground state. And then under those circumstances, you can write that the pairing energy is this constant G, which is the strength, about 20 MeV over A, as we showed before, times the number of particles minus the number of particles which are not there. This is the seniority that you were just discussing with P. and times the degeneracy of the system. The larger omega, so if you have a P3 halves or you have a I13 half, the pairing correlations will like the I13 half better because omega is larger. So you can gain energy by having more particles, more degeneracy. So you can rewrite this in a many different ways, but essentially you can approximate this simple expression if you are in a large shell, much larger than essentially when you can essentially for seniority 0, you can write this as n over 2. So I rearrange that in g omega, which you can now again rewrite as the number of pairs, n over 2 times twice a gap. So this is the energy that costs you to break a pair, and that's so-called the pairing gap. And essentially, you see the argument we were having just before, this goes like the number of pairs, and the reason is because they actually need to be very close to each other, so it's only those pairs that are correlating that contribute to the pairing energy. And you saw that early before for the case of the P3 half, and I saw an example that you did yesterday for the I13 half, if I'm not mistaken, to calculate the energy of the ground state. Now, an interesting thing was pointed out that by Chris Heide and others in this reference here, which is the fact that although the spectrum I'll show you here before looks very similar, when you look at the actual binding energy of the system, it's not. Actually, if you look at the delta interaction across a shell, the delta interaction continues rising while the pairing has a parabolic shape that bends over, because when you close here and there is sort of similar, giving the symmetry around each shell. And the reason why is that is because although the delta is a very short range interaction, it has all the other multiples on it, and as we will see next, the other multiples take advantage of the longer range, and now the energy can increase more than that with the number of pairs that we'll see next. So this is a picture you've seen based on this simple seniority with a constant pairing matrix element. There is a characteristic even gap. That's the gap that Bohr, Mottelson, and Pines observed and led them to propose the BCS approach to nuclear. You see the state here, the ground state, spin 0, strongly bound compared to the rest that lies somewhere there. And in this simple picture, if you now add a particle to it, as Pete was arguing, it lies right there at the same energy, if you like. And while a sort of a linear extrapolation, we put it in here, if it was just a linear relation as shown by the n over 2. So the next even lies there, and this distance again is twice the gap. You have an odd system, it's also there, so this is twice the gap. So this already suggests a way for us experimentalists to determine the size of this pairing gap. I can take an odd system and compare to the average of those two evens, or I can go to an odd system and compare to the average even, and look at that distance and determine a quantity which resembles that gain in pairing energy due to the delta or pairing interaction. And of course you can do that. And for example, if you look at things, let me go, yeah, you can do that. You will go to Bohr Mottelson, for example, or any other of the textbooks in nuclear. Then this is derived, say, for protons here, and you can see this nice expression here that sort of correlates the data, and you can see the gap in this. They parameterize this as something of the order of 12 MeV over square root of A. So indeed the gap, as we argued before, because the gap is strongly depending on the strength of the force, that strength we argue was about 20 MeV over A. The gap is not completely 1 over A because it's not exactly the strength of the force. It goes down slower than that 1 over A is a square root of A, and therefore you see this decrease in the data. So again, as we argued before, I mean, this average interaction at the beginning, we say decreases with A, and you see that also here. The pairing correlations here are less strong than they seem to be here. And the pairing gap, if you go back to the expression we had before, remember that includes not only the strength, but the degeneracy. And the degeneracy increases the larger the system you have. For example, in lead 2A, you will see an I13.5 level, which you don't see in lithium. And therefore, the gap will increase with omega, but omega increases less faster than G, and that's why you see the gap going down still with the size of the system. And coming back to this plot, the argument was you will see something which resembles a 0 plus and some excited state at an energy of 2 delta. And you can see, for example, the example that I wanted to show you is the thin isotope, which are the classic example of the seniority scheme or BCS condensate. And you see the 2 plus energy is very, very smooth. And all across the chain from 100 to 132, it's about 1.3, 1.4 MeV. If I would estimate twice the gap, it will be here. So it's actually a little bit less. And the question is why that is. And that's because, of course, as we'll argue next, it's not only pairing, but there is something else, which is the quadruple correlations that we discussed before. Yes?
In 128, say 1469.
The what?
In 128, it says 1469.
Must be 11.
It probably 11, sorry. My bad. 1169.
It's not, well,
But you see that rather constant, and this is indicative indeed of the presence of pairing, because pairing washes out, as we argued before. If you mixes all the levels and then it sort of makes everything look the same. Not at tin 100 and tin 132 because they are not enough to break the shell if you have only one disk.
I was just going to say, why aren't we plotting the energy divided by A? Or is that what's happening is just...
You mean in this here, in this plot?
No, in the pairing plot. Or I guess it's just G that depends on A.
If you have in this simple model, as you can see, I have defined the gap as G omega, and the reason because you have pairs, and we will see this afternoon in the activity where you actually will solve this problem numerically. Essentially, the pairing correlations thrive by scattering pairs from one level to other. And the more the generality you have, you can scatter. If you have only one level, the next one half, you cannot scatter anything. It's just there. It could be, it's like the high spin. You can have an isomer. The isomer is very, very bound, but it's not, it's very unique state. It's just one pair. Here you have a very mixed wave function that is the mixture of all pairs. We'll see that this afternoon when we look at the wave function. Now in this plot, I just put a constant pair. There should be actually a little dependence here because the gap depends on the square root of A, and so it will be the square root of say 100 compared to 132, and the gap will go down a bit. But in this small scale, it's probably not large. And so yeah, I'll show you that gap when you look at the overall picture. Now you see locally you have large fluctuations for that because at the end pairing is not so strong that it washes everything out. You still have left some shell effects there or quasi-particle effects that still give some identity to each nucleus. If, as I said, if pairing was so strong, it would be very boring. Now, of course, this parametrization of Bohr-Mottelson has been around for many years, and a quick estimate, of course, 812 over square root of A will put you close to where we should be. But there are other prescriptions here, at least one that I like in particular in this paper. And I like it because actually, if you were to use harmonic oscillator wave functions, then G, we say, goes like 1 over A, and then actually in the harmonic oscillator, omega goes like A to the 2/3. So then the gap should go like 1 over cube root of A. And I like that parametrization myself because they do pick that one. And of course, because we know that the mean fields depend on the mz or isospin, if you like, then there is a dependence on n minus c here that is taken into account in these more detailed expressions that go beyond the simple estimate of Bohr-Mottelson if you want to have that at hand. You see here, this seems to be a little larger for protons. We will go back to that on Thursday, but I'll keep that in mind, try to think why would it be that this main strength here is larger for protons than it is for neutrons. Okay, all the levels which are below the Fermi surface are occupied. The levels that are above the Fermi surface are empty. That gets changed because of the pairing correlation, and you have a continuous excitation of particles going back and forth through the Fermi surface, and actually be a mixture of both. So the idea of the activities on Thursday will be to solve a more realistic case. This is the example we will try to discuss, and we'll take some levels which may be appropriate for some region near lead to OA, if you like, and we'll try to solve those equations. But so essentially the structure of the problem is one where the ingredients that you remember in this Hamiltonian is the constant G, which measures the strength of these correlations, and the single particle degree of freedom, which is the distance of the single particle energies. So contrary to the electron system, this energy distance here is not negligible with respect to G. and the competition between pairing and single particle becomes more interesting. And actually that will be the subject of most of the activity this afternoon. But what can you say even if you don't solve the VCS? So that's the distance, and this control parameter x, which is the constant of the strength, and if you remember the degeneracy, the gap was g omega, and then the other energy scale is the distance between levels. This is some kind of control parameter that will drive the system from one limit to the other. So what happens if x is very small?
Single particle behavior
Sorry?
single particle behavior will dominate.
Exactly. See, if either the pairing strength or necessarily the distance between the levels is very large, that number is very small, and then, as he said, single particle dominate. And actually, this is so in nuclei to some extent, because there is a problem that you guys will solve, try to estimate what X is for nuclei, and that's why lead 208, for example, is still magic and is not washed out by pairing. And so when you solve the equation, and if you have, imagine that you have this set of levels, so you have a P3 habits, and you solve the single J. Pete showed you how to solve that. So X very small. What is the structure of the pairing gap that you will see? And it's already shown here, so you don't have to go very far, but do you understand why it would be? So essentially, if X is very small, you go through the shell, so every time you hit one of these levels, you hit a single shell. And you know how to solve that because Pete already told you, and so you see the little parabolic behavior of a single shell is maximum at mid shell with a maximum here, which is essentially omega over 2. And you see, for example, for the F7 half and so forth. So this is the way it looks, 7 half, 13 halves. Now if G is very large, which means that essentially G is so large that this little d here doesn't play any role, then you're going to see essentially a big shell. All the shells are collapsed. That would be why, if you were to have a strong pairing interaction, nuclei will all look the same. They will look all sort of like this. Just a big shell. But in nature, actually, with this G of order 20 of Ray, it looks sort of like in between, and you see still some effects that are left over, and we'll see that in the program tomorrow. In the same way, you can look at the behavior of the Fermi energy, if you like. If you have a very small value, you feel the level, then you jump to the next one, then you feel the next one, etc. And it's a ragged, broken line. In the limit of strong pairing correlation, it's a big shell essentially, and you just feel it smoothly all the way through. In the middle is something which still may show effects of the shell, but is somewhat washed out from the sharp Fermi surface of the single particle picture. I gave you before some pairing gaps that people like Jensen's and Gregor Hansen's describe. In the VCS approach, you go a little step further, more microscopically, and you actually look at the values of the pairing strength, and it's not surprising again that the pairing strength depends on whether you have neutrons or protons because of the potential changes with isospin, and therefore those are expressions that people have used to study by fitting pairing gaps in regions of the nuclear tail. So there is a constant isospin dependent, about 20 MeV as we said before, but there is a correction due to the isospin in terms of N minus. So we'll try this sometime tomorrow in the hands-on activity.
Thursday, you mean?
Thursday. Okay, so we argue, or Molinari, Schiffer, and True argue that the two ingredients, the most important ingredients of the residual interaction were these two. And we discussed so far the pairing part, but then there was the other part, the quadruple. Now, at this point, let me stress that nuclei are more richer than these two ingredients. I think what these people tried to do at that time is to extract the main drivers. But you know, lead-2OA is an octuple form. So there are also other terms in interaction that will appear. So we are talking about the major ingredients, and of course the details still there, but this is the major framework, so-called pairing plus quadruple approach. So we look at the pairing, and for that approach, we argue, well, pairing the nuclei in a state of angular momentum zero is the one that actually becomes more efficient, and therefore the pair wave function is written. Now if I look at this one, now you realize that the P2, when I plot that as a function of the angle, has a range which is much larger than just 180 degrees. So in fact, if you have these orbits again, a la Schiffer-True, where you have these angles given by the plane of the orbit, you can estimate that the angle separation of these orbits actually goes like 1 over the square root of j. So the larger the j, the smaller the separation of these orbits. And if you have actually an interaction which sort of likes to be, actually the P2 term has something of the order of 90 degrees, if you look at the at the plot of the P2. Then if you can put them in such a way that the angles of this is smaller than 90 degrees, then you make a strong correlation, because they are close by, they still feel that. And it turns out, and maybe, I don't know if this was discussed by Rick or Mark, you can imagine the aligned coupling scheme when you put all of them in orbits j, minus j, j minus 1, etc., trying to put the particles in orbits that maximize that overlap. And if you were to have that interaction available to you, then you can convince yourself that now is not only the next pair, that the next neighbor, but you can actually find out that the quadruple force now goes like n squared times v2. And so then the consequence is the following. You have the two terms, you have the pairing term and you have the quadruple term. And now the two of those compete, and there is an exercise that will work this afternoon. You guys will have to solve it. If you were to have some conditions for which at some point when you start to add these valence particles n, there could be a place where n takes over. And although when n is small you are dominated by this, at some point there is a change where the quadruple dominates. And you can show the condition, you have to solve that this afternoon, but essentially what happens is if you start to be dominated by the quadruple, you start with a pairing coupling scheme, we have a 0 plus well depressed. Now the quadruple starts to take over the 2 plus, which is the lowest excitation generated by the quadruple force, comes down because it becomes extremely easy to generate that, and then you switch from the pairing coupling scheme to the aligned coupling scheme where you are dominated by this term compared to that. That doesn't mean that they don't coexist, because the scales are so similar in a way that you cannot talk about one without the other. So what does it mean? If you are near lead 208 or say tin 100 or tin 132, that's a good closed shell. But as soon as you move out a little bit, you will have quadruple, and that's why the tin change, the 2 plus, is not as high as it should be, because the quadruple lowers a little bit, but still is a quasi-particle system. Now, if you go now to the other extreme, you have many particles outside closed shell. The main role will be that of the rotational or essentially rotational state, which means the deformation takes on compared to the gap. But that doesn't mean there is no pairing by any means, as we'll show you later. Pairing still influence that because the scales are, and that's what it makes the nucleus very rich. All these three scales, so we have the single particle energy scale, we have the pairing strength G, and we have the quadruple strength B2. So these three are similar, and it makes it rich. And I think, I believe Rick and also John with the IBA already have shown you that rich that is, because that actually the IBA incorporates these ingredients in an algebraic form, which here we're trying to do with the hands-on, more sort of schematic way. So we'll work on that this afternoon. Now, I said that, so now you guys will tell me, then I go from tin 100 and I just add neutrons or protons for that matter, and then the system will come deformed. And well, that's something that already you learned is not true in the lectures before. So I have to be a little careful with that. This is just to show you, because of the dependence on the number of particles, you are actually going to be able to induce that transition. However, this matrix element there, this V2, actually is very strong for neutron proton and not as much for NN or PP. And the transition is driven by the neutron proton. We'll show you that a little later. So here, for example, I'll show you the case, one of the typical archetypes of these transitions, a real spectrum. This was sort of a cartoonish way, but you can see that indeed there is resemblance to data in the nuclear landscape. This is the case of the dysprosium nuclei. You start here with a nucleus that is dominated by quasi-particles and spherical systems. Then you see the 2 plus going down dramatically and changing from a sort of a spherical system to a rotor. And I'm sure that Rick have discussed that with you in detail. I'll remind you here a fingerprint for that transition, which was pointed out many times by Rick before, is that ratio which I show here as the 4:2. And you can see that's actually a very nice indicator of that something is happening. It goes from something which is of the order of, in the limit of pure pairing, where you have the 2 and the 4 degenerate, this value will be 1. And it goes from sort of 1 to 3.3 for a perfect rotor. So now I can go back to nuclear data in Brookhaven and ask, can you plot me R4 to R2? And then you can make this nice plot, and, beautiful actually. And now you see Augusto was lying to me, because you see I move in N or Z, and the system doesn't really come from. It's only in between, because actually the main ingredient for that is the proton-neutron interaction, and of course Rick and Kuku Hamamoto early on pointed out that there is an empirical correlation of those properties with the number of protons and neutrons. So that n squared that I showed you before should be more properly considered as an NP-NN, and that drives the system from spherical to deformed. Of course, the correlations here of quadruple type, they still remain, as we saw, for example, in the teens. Here there is a strong quadruple correlation in the form of the phone. Of course, this was discussed by Federman and Pittel when in their sort of unified description of deformation within the shell model. And again, it goes back to this strong overlap between spin orbit parameters of the neutron and proton, because as we argue, that geometrical overlap is maximized if the orbits are the same and they are on a t=0 state. They are very strong, and that makes that V2 in this simple picture very large, and it drives the system to be dominated by the quadruple. So this cartoon you probably saw, I borrowed it from Rick to actually show you in a pictorial way that in the vibrational region, you imagine the nucleus is like a sphere, you're dominated by pairing, and then the excursions of equilibrium are in the form of a vibrational nucleus. That can be associated with the potential in the terms of that deformation degree of freedom, minimized at beta 0, and then some kind of a parabolic shape, and the energy is that of the vibrator, 2+, 4+, etc. Keep that in mind, because that's something we will try to also extend in the pairing. Now you start adding the valence nucleons, and then at some point, as we said, because now the P2 terms, which goes like the n squared, starts to dominate, that changes this potential and starts to make some kind of excursion in this axis of deformation. It becomes flattened, and at some point it minimizes. So there is a transition from one which is spherically, and Rick, you probably discussed the sort of a transition.
Mark actually did.
Mark discussed sort of the so-called X5 and E5 symmetry, which
Was
are
it Mark or Jan?
Norbert.
Well,
Norbert.
That's like Mark or Jan.
So Norbert discussed this sort of critical point phase transitions, notably in the shape degree of freedom E5 and X5, where the potential underlying the microscopic structure is somewhat flat before it goes from this to that. In this limit, the rotor energy that goes like II+1. So you see, the energy of the excitations of the system are strongly related to the underlying microscopic structure, and therefore that is an indicator Then we will use this later, of course, when we look at the pairing problem. So, a rotor. You know that well. Quantum rotor expression II plus 1, and there is a moment of inertia. And so we said that even if you are dominated by the quadrupole, that doesn't mean that pairing is not there. And pairing actually manifests itself in the fact that if you were to calculate microscopically what is the moment of inertia of a set of nucleons moving in an harmonic oscillator, and you sum the contributions of the angular momentum of of each of those particles. Actually, this is called the English formula. We develop that in terms of the perturbation theory. You find that it should be the rigid. That's very impressive, isn't it? I mean, just you have a nucleus in an harmonic oscillator, you sum that up and you get the rigid. Like if you have a microscopic football and you calculate given the deformation, that moment of inertia, these guys should be the same. That's amazing. And then you go to experiment and you see, well, that's not what you find. Okay. So actually, and the reason is so beautiful and so simple, because now that we understand about pairing, and you see, you sum here the contributions of each single particle, you immediately realize, well, if these particles are actually going to be paired in spin 0, they cannot contribute much to this expression. And lo and behold, now you do this expression, but now what do you use instead of single particle here? Yeah, we introduced the quasi-particles a few slides before. Now you know how to work that. You use the quasi-particle formalism, and you write that English equation, and then you come up here with two things. First of all, you remember the single particle energies are changed by energies which are actually now very large because they start with a gap. And this expression gets modified by this, which now has the gap only. So this term goes down because this term goes up. And then not only that, you remember that because of the pairing correlations, these guys have only a very limited window where they actually can work because of the, oops, sorry. Yes, this is a problem with this guy here, sorry. Very sensitive device. There is the UV factors that we introduce. And therefore, in order for these guys to continue, they have to be available, because otherwise the UV will give you 0 here. And there are some ways of estimating this. I already done that for you. But essentially, what it is that this is the level now. Actually, I believe Rick has told you about that single particles in the deformed system are not called single particles, they're called Wilson levels.
No, that's tomorrow.
Ooh, I'm predicting the future then. Rick will tell you tomorrow that these are Nielsen levels, which are labeled a little different than the J of a spherical, but they are related to. But for you it doesn't matter, isn't it? I mean, it's just a bunch of levels. Now you know how to solve this because you know how to solve DCS. So it's just a question of using these labels, and then you plot the UVs and that product that I showed you before, and you see is maximized at the Fermi surface. If the gap is larger, of course, that Fermi surface becomes more dilute, and then you take action far away from the Fermi. If the gap's small, it's only those that participate in the Fermi surface. So when you do that in quasi-particle picture, the moment of inertia gets changed, and then you get a nice expression which is called Migdal formula. And you see that Migdal formula is very simple actually. There is a rigid term, so essentially at some limit you would expect that the system will change to that. And now the control parameter again, x here. So if the control parameter is very small, which is you are not dominated by pairing, this should go to 1 and get the rigid body move. Yeah.
So this approximation pops right out of that sum over quasi-particles we saw?
Yes, yes. In fact, maybe we can try to play with that in the hands-on activities if you like. So, actually, one can, once you do that, of course, you have to do a realistic calculation, if you like, to do the individual levels and do it properly. But we can go a little step further and take some values that we know. And if I take what I know about sort of G omega, which we already, and then I'm going to assume that in the harmonic oscillator, actually, and I would imagine Rick will discuss that tomorrow, some of these levels, maybe I'll anticipate something here. Sorry, Rick. I think I know what you don't you feel that I don't respect here, as I showed in the slide early, but if epsilon is here and I start with a J, it actually fans out. The slope of this is given by the quadrupole moment of that particular substate, and actually this distance here, or the separation, increases with epsilon, as you see, proportional, and it's proportional to that. So this is not very quantitative, but it's just qualitative for you.
Now I don't have to give tomorrow's lecture.
No. So D I will parameterize as the harmonic oscillator energy scale times epsilon, and then I will construct X, and actually look at some of the data. So if I go to the nuclear data tables again, look at nuclei which are somewhat, I would say, quasi-rotational, if you like. Yeah.
So still a little bit confused about this epsilon parameter. To me, from this definition up here, it seems like it's what we're defining as our quanta that we're putting into our harmonic oscillator. But then we have fractional epsilon down here. So I guess I'm not understanding it.
So actually, this is not the epsilon there is not the number of quanta. Essentially, these are the two frequencies, because now when you have a deformed system, you can describe that as two harmonic oscillators. So this is your nice deformed system, and then you can associate one frequency on the axis 3, and then either 1 or 2, which is the same, and that will be 2. So the difference between those two is associated with the deformation. So if you were to have epsilon 0, the two frequencies are the same as the frequency of the harmonic oscillator, which is spherical.
Okay.
The more you deviate from that, it makes this axis bigger compared to that, and that ratio or difference is related to the deformation. And you describe that in the Nielsen model by having two harmonic oscillators.
Okay, thank you.
That's the way Nielsen did it. You can have, in a more sophisticated way, an harmonic, a Wood-Saxon deform, and solve that. But in the Nielsen, which is I'm using here as harmonic oscillator, you will write it that way. And so so then I go to the nuclear data tables and I look at rare earth and
Sir,
that, yes,
so just interruption. Sir, if we go this X is very small, then it is go kind of shell closure type of things, right? So can we verify this formula, this rigid, this moment of inertia, there, because there the system will not behave as a rotor, it will behave as a vibrator, right? So how can we verify this model, because if X going to small, then this rigid,
good point,
right?
excellent point. Those with have a very sharp eye, we see some yellow points here, maybe not.
Yeah, okay.
You see yellow points here?
Yes, yes, I can see.
That is the verification of those, and I'll tell you that in a second. Do you see it? It's not good, I just realized it's not very good. There are a
You put it
few-
intentionally yellow.
So, I'll get back to you in a second. So I plot here a two-dimensional plot, which is the moment of inertia which I derive from the 2 class. So assuming that is a rotor formula, I know the 2 plus energy, so I can derive the constant in front of that, which is the moment of inertia. But I pick nuclei for which measurement, and that probably was discussed by Norbert perhaps in his lecture, or did you discuss measures of BOV2 and things like that? Yes, so from the BOV2 or the Q naught, I derive epsilon, the deformation. I plot this, and you see many letters there. This relates to many rare earth and actinides nuclei, for which there is both data on Q naught and J over J region. And then I compare with the rotational flow. And you see, well, it's smaller. Irrotational will be if the nucleus was completely superfluid. But it's not, as you see, because we don't lie here. But we are not there either, so it means that pairing is strong. But it only affects those nucleons which are near the Fermi surface, so it's partially superfluid, if you like. It's superfluid in the surface. And actually, if I take Migdal's formula, with my parametrization here of what X is, I can draw the blue that goes with the blue points, because those are the rare air regions. And you see here H omega 0 and G and omega depend on the A, as we argued before. So I take that on somewhat of an average. And then you look at here, that's the actinides, a little heavier. So then the black sort of shaded area goes very nicely through. So I think the Migdal formula does a good work in correlating the data with the assumption of pairing correlations in the way that we have discussed. Now, there was an interesting question there. How do you actually confirm that this formula gets to the rigid limit when I take X going to 0 and I have, as we argued before, a spherical system, so I cannot do it. But how can I make X also small? Actually, I can make X small with D if I make epsilon large. And actually, Rick will show you tomorrow in the harmonic oscillator.
Augusto,
Yeah.
if you draw out that far somewhere, the video doesn't capture it.
Oh, okay. So yeah, if I actually draw, and maybe I'll grab a figure for this afternoon so we can look together again. you find that because you have many levels, you start with this in the harmonic oscillator. It turns out that for particular ratios of this omega 2 over omega 3, in particular a 2-to-1 ratio, which means the axis is 2-to-1. There is also a large stability at closed shells, because these guys sort of make this. I'll show you a real nice graph. So lead-208 here, for example, is a very closed shell spherical nucleus, but they, for example, dysprosium-152 is a fantastic super deformed nucleus for which the ratio is 2-to-1 and it's deformed. But for that one, pairing again will be small, because now there is a large deformed gap, and therefore moment of inertia should approach, in this case, 1, which is what you just said. But we are in the other limit, and those are the yellow points, okay?
Could you show where the yellow points are?
The yellow points are derived there from some super deformed bands in dysprosium, mercury, and actually you probably have heard of shape isomers in the actinides too. Plutonium, uranium, they have a shape isomer, which is in the plot that that I showed you from Wick. You have a potential energy as a function of vega, which it looks like this. There is a minimum at about sort of 0.2, 0.3, and then it does sort of like this, but it's a second minimum, and this is a 0.6. Actually, 0.6 is equivalent to 2-1 ratio in the Nielsen mode. And this is called shape isomer, because it's the same nucleus, the same isotope, but the only thing, and this is very, very different from this state, and therefore is very retarded. You cannot connect them very easily, and that's why it's called shape isomer. It lives long because it cannot talk easily to that one. And that one is also here. Now for those, the formation is large. X, say for example here there is a uranium point, and it's a uranium point there. This is the normal deformed, this is the shape isomer, very close to region. So I think this picture was very nice.
Also,
Yes.
sorry, I missed the point how your gray or blue surface are calculated.
So I take this and I calculate a range given the fact that in this region of masses I go from erbium 150 to 70 something, so I use the age of those strings, if you like, and plot those limits from this formula. And the only variable in this formula is epsilon, because I know G, I know omega, and I know the parametrization of those with A.
So basically the width of the surface
Is the mass region of the rare earth that I use, and for the black is the mass region of the actinides.
So this is somehow related to the which shell you use to determine surface to calculate omega.
Yeah, correct. Now I can do the reverse, and that you will ask, of course, why don't you do that? Yes, I can actually do the reverse. And for assuming that Migdal formula is correct, because I believe pairing is the basic ingredient here, I can do the reverse and calculate the gap that I will require for these many nuclei in the nuclear table to describe the 2 class. Okay, and I do that again. I know the nuclear data, I took all those, and that's what I find. Pair gaps from rotational moment of inertia. Okay? completely different observable, and it lies very close to those gaps that Bohr models derive from massive. Unbelievable, this is fantastic. You know, really tells you that there has to be pairing. There is no question about it, isn't it? Because, I mean, this is really two completely different two completely different observables. One is moment of inertia of the two class. The other one is masses of the ground states are very nicely put into one single picture that is driven by the pairing. Now, of course, again, there are fluctuations and a structure there that makes nuclear very interesting in themselves, each of one, but the overall ingredient seems to be there as the pairing for it. I think I find this very nice. Okay. Questions?
Why is there multiple lines for?
Oh, because, yes, this is done, the way I do it is for isotopes. So I take just Z from, it's easy to grab that from SDEF, you get an isotopic change and you run it for those. Okay, so,
Also,
yes.
another question. In the previous slides, for example, for deformed bands that are constructed to a two-particle two-hole excitation that you can find in the super deformed band of calcium or stuff like that. How this will be, because pairing should be important.
Yeah, well, in there, you can actually estimate what, if you were to use that in the Nielsen model, you can estimate what the region will be and what you measure. And there you will find something that I will discuss a little later, which is called blocking. So, related to that, and the analogy that Bohr-Mottelson and Pines proposed in '58, it's not surprised that Mottelson and Valatan say, well, I mean, this is a superconductor. I know I break superconductivity with a magnetic field. So in nuclear, the analogy of magnetic field will be the angular momentum, because those will like to break the pair. At some point, I should quench superconductivity. So, well, how would that work? And that's easy to estimate. If you imagine a rotational nucleus for which there is no superconductivity, that's the red line. I squared, I mean, I'm assuming I squared, not I plus 1. Rigid moment of inertia, that's what we just say. But we just say pairing is there, so it cannot be that the picture. So actually for the nuclei in the ground state, I will start with the gaining energy, which is the correlation energy, usually delta squared over D. So I'm below what it would be the single particle ground state by the pairing of correlation energy. But what is the price that I pay? Well, the price that I pay is the fact that the moment of inertia is not the rigid. Actually, if we go back to my plot over there, I would say, I don't know, maybe a third of the rigid. Take your pick, whatever you want, a third. And so it's simply, then I get I squared over 2, I rigid over 3. And then when you do that, you see that those parabolas cross at some point. What that does mean? Well, it means that at that point, I quench BCS. All the particles will break. I rather give up the energy in pairing and put it in the rotation, and that will be the pairing phase transition nuclei as the Mottelson-Valatan effect. And people were very excited because early results from Sweden, Arne Jonsson, show a discontinuity of the energy as a function of a band, as a function of angular momentum. They discovered the quenching of BCS in nuclei. but actually it turns out that that was not the case. And the reason for that,
Sir, I just missed the point. How we get this I digit by 3 term?
where I put, oh, yeah, I put the 3 there because if I go back to this plot that I show here, I would say about a third, maybe a fourth, whatever.
Oh, okay.
Something which is not the rigid, closer to a third. And of the, I mean, even if you take half, it will move further up, but there will be a transition here into, depending on the nucleus, of course, as you saw, that depends on the actual nucleus you are in. But overall, I will expect a common feature that at some point Motteson and Valatan will take on. Now, the problem with this picture is that actually, as we said before, each single particle, each nucleus is its own identity, and some of these particular orbits are a little better than others in terms of Coriolis interaction. And that can be understood in a simple cartoon again. Here you have this pair of high J orbits, okay, say, or the J orbit. I'm not saying high J at the moment. I'm just saying that. And you see here, that's this parabola I squared over 2J. However, if I'm going to break that pair and make an aligned orbit like that, which now generates angular momentum by summing those two, you can show in a very semi-classical way, if you like, that this parabola starts now at 0 at the low energy, but it has 2 times the aligned speed. And you can see that they will cross there again, because it cost you 2 delta to make that, but in huge, large amounts of angular momentum. So actually, pairing, if it were completely not selective, it will generate the phase transition. But because the structure of the single particles, some particles are better than others, let's say, and the so-called Stevens-Simons mechanism takes on. And what you see is an alignment of one pair. And that actually generates a discontinuity in the band, because you start like this and then you switch to that, and you can confuse that with the picture before, which will generate a similar behavior. But the physics is not the same. It is related, but it's not the same. It's so-called backbending mechanism, and the reason why is that is will become apparent in a minute. And essentially, it happens when this term, which is the Coriolis term, J dot I, divided by the moment of inertia, becomes something of the order of the 2 gaps. So the first particle to align will be that one of the high J. The lower angular momentum will come later. Yes?
Can you explain why this quantity reflects the classical concept of Coriolis?
Oh, because the Coriolis force is essentially J, if you have a particle moving in a rotating frame, is J of the angular momentum of that with the angular momentum of the system. So the Coriolis force, or the Coriolis interaction, essentially is I dot J.
Okay, so I'm going to talk about that tomorrow. I don't think they. Has anybody talked about Coriolis yet? So I'll discuss it tomorrow.
Very good. Please.
So if I understood it right from physical point, so the nucleus is spin and spin, and then at some point the structure will change and it become something else in that phase transition.
Correct. Which Motteson and Valatan thought that it was just that if you have a superconductor and at some point you increase the magnetic field, they all ampere. Here, that will be the case. All the particles are paired, but suddenly at some point they start to break, all of them at the same time.
It's because they're like high speed?
Yeah, because when you have a gyroscope, if you like, a gyroscope, you know, they try to align with the angular momentum of the system. If you have a gyroscope in a little turntable, then you start to spin, the gyroscope tends to align with that would be the classical way. This is quantum mechanics, but still it goes into a phase transition. But it's not actually. What happens is these particular orbits align. Now we will go further because, as you know, those others will align at some point. So actually, will you discuss the crankinal
No.
picture? So this is more like an informative slide. It's not part of the lectures per se, but I thought because of the jargon of high spin physics requires some things that you may not be completely familiar. I thought of put it here as a dictionary. So essentially, you have, as I showed before, the information that we get is energy versus angular momentum. That's what we have. This is when you do gamma ray spectroscopy or particle spectroscopy, you have levels, excitation energy, and hopefully spin. So you have energy versus angular momentum. If you have those quantities, you can calculate a rotational frequency, which is related in classic Hamiltonian to the derivative of the energy with angular momentum. Now you do have the angular momentum because you measure that or determine that from the experiment. So you have actually that angular momentum as a function of frequency. And if you have angular momentum as a function of frequency, then you have moments of inertia. There is the so-called kinematical moment of inertia. That's the ratio of spin over frequency. Very simple. But then you can have the derivative. That's called the dynamical moment of inertia. This is di d omega. Okay, so we look at data experimentally, and we usually give you a moment of inertia. I1, which is the kinematical moment of inertia, or I2, which is the dynamical moment of inertia. Now, those of you which are versed in classical mechanics will immediately realize the connection of these to mass. So, in actually classical mechanics, you find you have the kinematical mass, which is the relation of P with V, but you can also have the dynamical mass, which is that response of the dP over dt, so essentially it's dP over dV. That's the second one, it's the one that goes into Newton's law. And that's the reason why we don't go to the third derivative, because we don't need it. All the dynamics is given by those two. Okay, you know those two, you know everything. So, and now, having introduced that to you, then I can show you some nice plots here, okay? And then this is the energy versus psi. That's what we have in the experiment, as I showed you before. You have that band there, that was the ground state band and the aligned band. And now the real band, depending on how those mix, will follow some kind of the orange pattern. And then if I plot angular momentum versus frequency, it will look like this. At the beginning, it will be a straight line, which follows the red. And then at some point it crosses to the blue, and that should be the same straight line, but hitting at 10, because I have two aligned particles. So is the dynamic of a system that has two aligned particles and then rotates. So it should extrapolate back to this 10, and then it goes from one to the other like this, depending on how they mix. Now, if I now take the ratio of I versus omega, I get the moment of inertia I1, And you see that that is sort of like a constant here, which is the moment of inertia of this part. And then at some point it jumps. So it goes up because the spin increases, then it goes down. So it comes constant, up, and then goes down. And then of course if I take the derivative, it's also constant and then a big jump. And you see this quantity is very sensitive to signal a phase transition of some kind of a change. And that was the indication that people were looking for to actually see whether there was a BCS breakdown or not. If you make the interaction of the bands rather small, then you jump suddenly, and actually this plot backbends, because you go from this curve and that's why it's called the backbending. If it is, the interaction is very, very large, then it's very smooth. So it looks more like this or even smoother depending on how the interaction of those two bands happen. Now, of course, this is a nice exercise, and of course, as I said, people show this experimentally, and this is shown here from that first plot. This was the band in dysprosium 160 as a function. They use h bar omega square here to make it a little better. You see, that's the rigid rotor value for that nucleus. The moment of inertia increases, and then suddenly a big jump. And approaching the rigid, everybody got excited. That's the quenching of superconductivity. But it turns out that that was not the case. And then you see many other nuclei here again, the sort of a backbending plot. This actually is the alignment plot. The I-13 have particles align very fast, and they give you this increase in moment of inertia compared to the ground state region where it's quenched due to pairing perturbations. I think somebody already asked, and this is an example that came later actually from Berkeley. You see here as a function of frequency in the case of erbium, the first backbending, that's one particle aligns. But people, when they say, if it's really an alignment, that was Stevens, of course, and then they went up and pushed the spectroscopy high, and then you see the second alignment. And the third, it should be more. So people now know that you go and align the lowest spin particles. And at some point, obviously, the question is when is, yes?
Sir, just after the first alignment, why is band going down? Because with frequency, then the moment of inertia going to be increased, and that should be.
This is, yeah, actually,
Second part.
that is a good question. I mean, you see here that actually the I2 or I1 that you plot, it goes up and then it goes down. At the region of the alignment that you gain a lot and then it comes back, it should come back to a value which is larger, which is the difference between this moment of inertia and that, and depending on what the moment of inertia is before or after, but the enhancement is at the crossing. Here, there's a large, and then you see it sort of comes back to a value that will be, but then suddenly another crossing comes online. So that means in the picture of band crossing that you saw there, you have one band here, then you have the other band there, then the other band, and so forth. And then you follow this, sort of the envelope of those minimums. And at some point, you would expect that you will approach the rigid when all the pairing is quenched, and you expect that at some point that will happen. Now, of course, I mentioned the analogy to other fields, and the fact that you align those particles here, as I just argued, doesn't mean that there is no pairing. In fact, pairing still plays a strong role. This in solid state physics is called gapless superconductivity. So these particular orbits do not see a gap anymore. But the gap is there in the BCS, so pairing is still there. It's just that these particles do not see the gap anymore. That's why they call it gapless superconductivity. The system is still superconductor, but those particular particles, because of this strong Coriolis energy, they just don't see it, and they align.
So
Okay,
it's
so-
not really quenching kind of things, right? So in quenching, we all the pairs breaking together.
At the same time, yeah, everything is just
Just
like in a
just
real
from
superconductor.
to just sharp change, but here it is not like that. If you go to have angular momentum, then the second pair will break. Okay.
Correct. That's why, because, you know, in electrons they sort of all the same. Here, as I said, each nucleon in each orbit has its own identity, and therefore they are not sort of equal. Now,
But still, how do you get this? I mean, you break two, so you break one pair, then you break another, or you, as you see here, you have a lithium kind the shells. But I still don't get why do you increase angular momentum, your energy drops.
oh, because
Is it because
you,
stretching?
the rotational energy goes with the rotational angular momentum. So in your Hamiltonian is actually r squared over 2j plus the single particle energy. And this r now is I minus j. And if you have that one 0, then all is collective rotation. If you now split that r into the total and j, you gain 2j units of angular momentum that doesn't cost you any energy, except breaking the pair. When that energy, that rotational part, becomes comparable to the gap, then you flip over. Because it costs you less energy to align, that's you can do with the gyroscope. Huh? If you spin very low, the gyroscope is running this way, it just keeps there. And at some point, the gyroscope, boom, aligns when the rotational Coriolis force compensates the loss in the internal energy. But what happens, of course, is the following. In the picture of that Nielsen model that you will see tomorrow, this doesn't see very well. You see, this is yellow again. Yeah, there should be a yellow, a yellow feeling here to indicate that this was sort of full. So that's the Fermi energy somehow, and I have all the particles here.
Okay.
And imagine that they are all occupied, and then I have a pair of nucleons here. The pairing interaction scatters that pair into those levels which are above the Fermi surface, and therefore I can take part of that correlation. But now I just told you about the alignment. At some point, these particular 642 are the I13.5, as you will learn tomorrow from Rick. Then you align that pair. It means that you have to put one there and that there to give you the angular momentum. Now, when I occupy those orbits, you see I cannot scatter anymore to here, nor there, because of the Pauli principle. So now I'm blocking some of these levels, and my omega, which is not that omega, that's an omega that you will learn tomorrow, is the projection of the symmetry axis, blocks this orbit. So now my omega is smaller, which means that the pairing gap will go down because g omega goes down. And at some point, after I align many particles, I will not have any omega left, and pairing should go really to 0 at some point. And we will expect that to happen at very high angular momentum after many particles have aligned. Now remember that this is a phase transition where that control parameter x, which was G omega over epsilon or delta epsilon or D, whatever. This is a phase transition. So at some point, if say in the ground state I am with an x which is larger than 1, and now by blocking I make omega, then at some point I will go from x larger than 1 to x smaller than 1. So pairing will be quenched, even if all of them are not aligned, okay? Because I made x smaller by changing the omega. So I could write the phase transition. So maybe after the third or fourth back bending, if you like, the system will be quenched because x goes down and is below the critical value. Now, that means that is below the critical value doesn't mean that there is no pairing, and the relevant degree of freedom there is what we call pairing vibration, which is what we are going to discuss now, if we have time. Okay, so blocking, there was a question early on about these rotational bands which involve the quasi-particles, excited quasi-particles, and that you can look by looking at multi-quasi-particle states which are formed in low excited isomeric states, which in this particular case are rotational because they form a rotational band in a high K component. And this is a plot from a review article by George Rakulis, who sadly passed away not so long ago. The group in Canberra look at this in very much detail, and they are plotting here the Migdal formula, which I just showed you before, and the J0, they call it Harris. That's an expansion that was derived by Harris. Essentially, that axis on the left is a fit of experimental data by a Harris expansion. And then you see here, as a function of the number of aligned particles, this will be the ground state, and so forth, 2 quasi-particles, 4 quasi-particles, etc. And you see the moment of inertia, these masses are very similar. So the actual experimental data increases with the number of particles that you have aligned in the isomeric state, which is because of blocking. It quenches delta, and therefore it makes the moment of inertia larger, approaching the rigid moment of inertia, which actually is here in this line. And they find an empirical formula which relates the gap, say, when you have an aligned 2 quasi-particle state, appears to be 75% of that of the ground state. So this will be 2, ground state 0, so about 3/4 reduction. So then you can go and see, well, now I have 4 quasi-particles, that will be 0.75 or so forth. So at some point, the effective gap that you need to reproduce the moment of inertia is quenched, indicating that indeed, at some point, pairing is gone at high speed. Yes?
In these plots, I don't really get what kind of information you get from comparing the Harris parameterization to the Migdal parameterization.
So here, I mean, as I said, I could have redone the plot, but essentially J0, so what they do in the Harris expansion is that they assume that the energy as a function of omega is some kind of energy plus 1/2 J omega squared. And you fit this from the experimental data. So essentially, it's an experimental measure of the moment of inertia. Usually in the cranking, you use the Harris expansion because you do it in frequency rather than in angular momentum. So you have that, and then I go to my Migdal formula, the one that I showed you earlier, and determine the gap that I need to reproduce this. So when I have no aligned particle, here I know the structure, so I can calculate what the gap and so forth. So in order to reproduce this data, I need to put in the Migdal formula a gap that is reduced, and that is plausible because of what I said just before. Because of this blocking argument, I will expect that the gap when I have a one quasi-particle, an isomeric state here made out of those two particles, this blocks pairing is smaller and so forth. So this is an empirical way of assessing how much the pairing gets quenched as you add particles. And this is the way they parameterize that in the... Essentially what we expect is therefore, as in superconductivity, that at some point the gap with angular momentum or frequency will go down, and at some point it will be zero. Now, it never gets zero in the sense of it will still have dynamical pairing here. And that's what I'm going to discuss next. Because the fact that this BCS gap goes to zero doesn't mean that there is no pairing. It means that the nature of pairing or the dynamics of the pairing is in the form of a pairing phonon. That's coming up next. How are we doing?
10, 12.
Yes. So let me go back to that plot that we discussed earlier. This was introduced early on by Rick. So you have some kind of potential. You have a potential as a function of this degree of freedom, which is the geometrical deformation. You have a vibration, a potential like this. You change n or n and p, and you go into the form region, then you change from this to something that has a non-zero deformation, and the energy was an indicator of that transition. Now, we talk about pairing. Actually, we argue about this control parameter here, which is proportional to the omega g divided by d, and if this is large, then x is large, d, or you can go from. Now I'm plotting a potential as a function of a deformation, but the deformation, of course, is not in real space in the sense that I'm not looking at the deformation of the surface of the nucleus. I'm looking at a deformation, if you like, of the pair field. If there is or no a gap solution. And actually, there is an analogy that you can follow, and then if it were a vibration system x less than 1, then you have something where the gap is sort of this alpha, which is the gap over G, is non-zero, essentially. That will be a BCS solution. Here the potential is at 0, which means that there is no permanent deformation in the pairings degree of freedom. At some point, if I change the control parameter, we argue that we will actually transition to a condition where there is pairing. And that's something that will be part of our problem activities this afternoon, is to study this transition where you go from vibrations in this so-called gauge space to rotations in gauge space. And actually, there is an analogy that was, let me go there, discussed in detail by Broglie and others, but essentially between shape transitions and pairing transitions. The angular momentum, as we saw, was the key element that allows you to look at energy versus angular momentum and decide whether it was a vibration or a rotor. Here you imagine a real space. These are the Euler angles, and the system rotates in space and generates some kind of rotational band in physical space. Here, the equivalent of angular momentum is the particle number, and the orientation of the system is specified only by one Euler angle, if you like. There are no the Euler angles of the rotational system. Here is just one angle, and because the way that translates in a transformation that resembles a gauge transformation in particle physics, they call it gauge space. So actually imagine that this deformation is the deformation, if you like, of a Fermi surface, and there is a pairing or no pairing. You can imagine your Fermi surface to be sharp or not, depending on whether, and if you have a pairing gap which is finite, then the Fermi surface is diffuse. If you have a pairing gap which is zero, the Fermi surface is sharp, but it vibrates collectively due to the changes in the pairing value. Now let me go back, because I show you here these potentials, and does it really work that way in reality? And we have looked into that with my colleague at Berkeley, Rod Clark, and then you can see actually a simple result that shows you that potential as a function of this control parameter. And lo and behold, when the parameter here is small, you see a parabolic thing. When the parameter is large, you see a minimum, which indicates that the pairing gap is non-zero. And in between, you see this sort of called critical phase point, which actually you discuss E5 and X5 with Norbert early on. I can tell you that this is called E2 because it's a pairing degree of freedom. So you can see that this is not just speculation, it comes up naturally in the system. Now, this violation of a spherical symmetry in physical space, Rick showed you, and I sort of reminded you today, that translates into a characteristic dependence of the energy of the system with angular momentum. And I will argue next that that should be the case here. For example, this is a more realistic calculation by Van Sorensen for lead 208. We know lead 208 is a very close shell system, so you would expect an harmonic type of oscillator there, and indeed excursions of the gap centered at zero parabolic. But if you go to the TIN 120, which I gave you as an example of a nice pair system, indeed looks like a pairing gap around 1 MeV, as we saw in the figure before. So this the energy now, as we argue, is characteristic. We will pick up again this afternoon on this, but essentially, if you are near lead 208, we talked about a phonon. And the characteristic of a phonon is a linear dependence of energy with the angular momentum, or in this case with the number of particles or pairs from the closed shell. And you see that the ground states of this system do indeed follow a linear pattern, which is near lead 208. So proportional, and we will explore this afternoon. On the contrary, if you go to the tin region, this is again the tin 130, from tin 100 to tin 132, and you plot the binding energy of the ground state, you find that indeed, actually this fit, which is shown there with the dashed line, is very close to a square approximation in the number of particles, which is the signature of the rotor. Instead of being I squared, the analogy is the number of particles, and that tells you exactly that, follows very nicely what you see in experiment. And the purpose of the activities this afternoon is to actually study this in the form of a single problem of 2 levels, which is easy to solve, and we will do that this afternoon in the activities. And to conclude, I think it's time for lunch, but I couldn't imagine a better way to give you another perspective of this, particularly with the excitement of the Higgs boson discovery and the Nobel Prize. This is a very nice paper from Max Planck Institute, and you can look at that. But essentially, let me show you the figure that they presented. And you see here, that's in superconductivity in traps. So essentially, you've been seeing the so-called Mexican hat potential of Higgs. And here you show the control parameter, which in this case is the current they apply to the superfluid system. And this is actually the fact that the Mexican hat deforms in non-zero deformation. That's the so-called Goldstone boson. That's the rotation in tin pairing rotation. This is exactly that picture. The system becomes deformed, and it actually generates rotational band. But this is the Higgs mode. So for those that were developed this constant, they were ahead of the time. The Higgs boson was the pairing vibration. It's the same mechanism, if you like. The difference, of course, is that we are in a finite system. But essentially here, they showed actually that Higgs mode in this paper, and this will be the pairing vibrations that we are studying in nuclear. So this is my last slide today. And so we'll get back this afternoon and try to understand a little bit better this system with some hands-on activities. And thank you very much.